So we're going to do the vibration and quantum combination bands today because there's some funny little peaks that show up in the spectrum that if you were to get in there and look at the assignment of those spectral peaks, you would say, well, this doesn't fit any of the fundamentals. And I had mentioned that in the mid-infrared, we're dealing with fundamentals, and mainly I was talking about that we weren't going to be seeing a whole bunch of overtones and so on, but they do show up. There's a few that show up, and there's a few things called combination bands that show up. So if you're looking at the just this FTIR of automobile exhaust, pretty simple thing, CO2 and water and a little bit of carbon monoxide, but that up here we see these extra peaks, and we know it's a small gas phase molecule. And this water here, this is this sort of broad band here for water. There's these rho vibrational peaks. If we zoom in on those, we see P and R branches. So we know it's a small molecule. We know it's a symmetric molecule because we see distinct P and R branches. So we know it's not water. Okay, and so we do the math, or we did the math in the past, and we realized that those are combination bands for CO2. So here's the CO2 molecule, and it's two fundamental stretches that may show up in the mid-infrared region. One of them is Raman active. That's the new one, which is Raman active. So 1388, that would be the symmetric stretch. And then the asymmetric stretch is 2349. And the asymmetric stretch is in infrared active. So this one goes here. That's got A1U symmetry. It's along the z-axis. And this one goes here. And it's A1G. So you have an even ground state and an even upper state, and light is odd. So you can't directly hit that one. You have to use the Raman technique to get that one. Okay, so then these are our fundamentals. And notice neither one of those frequencies is in the 3600 range. So those rho vibrational peaks can't be the fundamentals. If we look at what they're related to, if we were to run that automobile exhaust through something that absorbs CO2, say, then those peaks decrease. So we know that those peaks are associated with CO2, and we know that they're not the fundamentals. And so we had to figure out what is going on with those peaks. So they end up being combination bands. So remember, we have this kind of notation. We have 3n minus 6 vibrations, and so this is going to be nu 3. So we have going from 0, 0, 0 to 0, 0, 1. Notice we're still in the ground state for vibration 1, still in the ground state for vibration 2, but we have 1 unit of excitation in vibration 3. So does everybody understand the notation? The 0, 0, 1 band, that's going to be just a single excitation, the fundamental, in the third vibration. We call it nu 3. So the vibrational frequency of the third normal mode of vibration. Okay, and that one is directly excitable with infrared light. This one here, again, 0, 0, 0 to 1, 0, 0. So that's the single excitation in the first vibrational state. So we call that nu 1. And so that one is achievable by Raman spectroscopy. And the combination, or we have also the vibrational frequency of nu 2. And so here we're going from 0, 0, 0 to 0, 1, 0. So that's the vibrational frequency for nu 2, and that's around 700 wave numbers. You see over here, this nu 2 is 700 wave numbers. Okay, and then we have this combination band. So the 3684 peak was identified as this 0, 2, 1. So do you see the combination? It's 2 nu 2 plus nu 3. So that's the combination that gives us this frequency. Let's see if we can figure that out. That's 2 times 700 plus nu 3, which is 2300. Okay. So 2300 plus 700, that's going to be 3000, plus another 700 is going to be around 3700. And you see this is pretty close, 3684. It never hits exactly, but it's really close. So 3684 matches 2 times the 700 band plus a 2300 band. Everybody see that? Okay. And then here's the symmetries of those. Yes?
On the test for the combination band questions, are they going to be more like that, or are they going to be more like 24 from the homework?
24 from the homework. Let's see, I think I printed that off. I've got the homework in at the end of this lecture. And so what we'll do is we'll finish. This is really a pretty short set of notes. So when we're done with that, we'll go through the homework. So just go ahead and read it out, though, for me.
Okay. It says the vibrational frequencies of CO2 are V1, 13,800 centimeters, V2, 667, V3, 2,350.
Yeah.
Would be the frequency of combination designated by V1 equals 1, V2 equals 2, and V3 equals 3.
Yeah, so you're just adding those up, and notice how this is the quantum states here. So this is V1 equals 0, V2 equals 2, and V3 equals 1. Okay, and so since V2 was equal to 2, we multiplied that frequency by 2. And so you go through whatever quantum state you have for each of those, you multiply that frequency by that number of quantum excitations. Okay, and then V3 equals 1, so we just have 1 times the 2300. And so you just add all of those up, and that's what the new frequency will be. In this case, it was 3700. Okay. And so we can look at the symmetries for these things, and they're pretty crazy because we have all kinds of symmetries from all of these different wave functions. So here we have going from 0, 0, 0 with Z polarized light to 0, 2, 1. And here are the symmetries associated with that. So the ground state, 0, 0, 0, gives us all 3 of these top rows. Z is A1U, and then we have the new 3 is A1U, new 2 is these 2 here, and new 1 is A1G. And so we can look to see if the direct products of all of these functions, think about it, we have really, we're not using new 1, so it could be taken out, but new 2 and new 3, we have all kinds of wave functions associated with this. We've got the ground state wave functions, and then we have all of the excited state wave functions. Now, how a single photon of light can cause it to go to excitation in 2 different wave functions in the vibration, that's a mystery to me too. Yeah, the symmetry works out, and so this photon of light comes in, and this molecule then has excitation in 2 different modes of vibration. Yes?
Is there 2 V2s because it's 2?
Yeah. And so that's just showing you the math. Okay. All right, so let's look at the symmetry breakdown of this. So this is our transition dipole moment integral to look at the intensity. If this is equal to 0, then this isn't the correct assignment of this peak. So if we looked at all these symmetries and it wasn't allowed, then we just have to find another combination that gets close. So this is one of the checks that we use whenever we're trying to figure out if this is a correct assignment of this combination. And so then we have all of these symmetry elements written out, and we just start doing them. You know, A1G times anything is A1G. You know, I'm sorry, A1G times A1G. It's just A1G times anything gives you that thing back. And so all 3 of these are going to produce A1G. And then we have A1G times A1U gives A1U. Okay, and then we have anything times itself is going to be top row. So these next 2 multiplied by each other will give A1G. And if you're trying to keep up, scrambling to write this down, be sure to remember that there's the video. So if I leave you behind a little bit so we can get to reviewing for the test, you can go to the video and get these things written down. Then anything times A1G is returned, because A1G is kind of like the identity. It's all plus ones. So we get E1U, and now this next one we need the direct product table for. So E1U times E1U actually is giving us these three. I thought I had the direct product table pop up over here. Okay. So notice how E times E gives us these three here. A1 plus A2 plus E. And then U times U is G, so we get G's on all of those. And then we have A1G times all of these three elements. So A1G times, anything is going to return that thing. So we end up with this result from all of these symmetry operations, and we see that it contains the top row. So because it contains the top row, this is not equal to 0, and so it's, at least in theory, it's allowed. We don't know the intensity, so there's a whole lot of combination bands that should show up in the peak, in the spectrum, but their intensity is just low. So they're probably there, they just don't show up because they're not very strong. The ones that we're showing here for CO2 must be strong enough. Their actual intensity is much different than 0, and so we can detect them. Okay. So that's an allowed. So we've assigned this one here, this 3684. We've said yes, that this assignment is allowed by symmetry, and the frequencies of the different vibrational motions add up to this number. So we've assigned that one. Okay. And so let's look at a different molecule to get some more interesting combinations. So here's the normal modes and frequencies for acetonitrile. It's a C3V molecule. So we have a triple bond, C, and a methyl group. Okay, hopefully you could do all of that. You've got the molecule here, you've got the point group here, C3V. Here's the coordinate system. The z-axis is the axis of the molecule, the threefold symmetry axis. And in C3V, you just have A1, A2, and E. And all of the vibrations in this molecule are either A1 or E. Now, how many vibrations? This is on every test, right? So how many vibrations does this molecule have? 3n minus 6. So let's count up the number of atoms. That's what n is. So we have 1, 2, 3, 4, 5, 6. So n is 6. 3 times 6 is 18. Minus 6 is 12. So we should have 12 vibrations. These are all of the normal modes of vibration, and I only count 8. So where's the other 4? Yeah, the E's are 2. So the E's, each of these count as 2. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's all 12 vibrations in the molecule. Yes?
Why does E count in twice?
Because in the symmetry of the molecule, take this, this motion here, maybe this carbon is going this way while all these other atoms are going this way. That can happen in the Y direction, but it could also happen in the X direction. But it's the same motion, just rotated 90 degrees, and that has the same frequency. So we call that, since it's the same frequency, it's doubly degenerate. And so all the E motions are doubly degenerate. They have a G of 2. If you're doing a Boltzmann calculation, that G in front is the degeneracy. And all of the E motions would have a G of 2. So they're just double energy levels because there's no difference in the X or Y direction in a symmetric top. So whenever there's a C rotation axis that's threefold or greater, so C3, C4, C5, and so on, the X and Y directions are going to be the same energy. So it's a good question. And so this is all 12 vibrations. And here's the spectrum of acetonitrile. Quite a lot of peaks. Because again, it's a symmetric molecule, but it's not what we call centrosymmetric. It doesn't have an inversion center. When they have an inversion center, then you have Raman and IR peaks that are mutually exclusive. And so it essentially cuts the number of peaks in the infrared by 2. So we might only see 6 of those 12 in the infrared, and we'd see 6 of them in the Raman. It's not always perfect like that, but if it's a Raman peak, it's not in the IR. If it has an inversion center. This molecule is a symmetric molecule, but not centrosymmetric. It doesn't have an inversion center. So it has all of these are Raman and IR active. So we could have as many as 8 peaks in the infrared because these have the same frequency. They're always going to be right on top of each other. So we should have roughly 8 peaks in the infrared. So we come in here and we see almost all of them. We have nu 1, nu 2, nu 3, nu 4. The old way of numbering these was from high frequency to low frequency, symmetric first, and then asymmetric second. So notice all the A1s. These are the symmetries. So nu 1, nu 2, nu 3, nu 4. Those are the 4 symmetric stretches that we have. And then the asymmetric, the E's, nu 5 here, nu 6, nu 7, and nu 8 is actually below the window of the mid-infrared. And so where these other peaks come from, well, they're combinations. So we have this combination band of nu 3 plus nu 4, and we have this combination band of nu 7 plus nu 8, and we actually see an overtone. So there are more than 8 peaks in the infrared spectrum, and so we had to figure out what's going on with those. There's a few other peaks here. This right here, these little mess right there, there's something strange there, a few things there, and a few things there. I confess I took this and my acetonitrile is kind of dirty. It's got some other compounds in it. All right, so when you open a fresh bottle, like brand new, you don't see those peaks. And so we know, okay, those are impurities. So sorry for that, but that's what it is. And so here's, so let's look at these combination bands. So here's the nu 3 plus nu 4 combination band in acetonitrile. I'm not showing all 8 quantum numbers. I'm just showing the 2 that change, because it would be 0, 0, 0, 0, or whatever on the right and the left, and so those would all essentially cancel each other out. But we have the ones that change. We have nu 3 and nu 4 going from 0 to nu 3 and nu 4 going to 1. And so it's nice though that nu 3 and nu 4 are still top row, so it's top row all the way across. So this one's pretty easy. Again, by pairwise combinations from right to left, we end up with A1, which is top row, so that's not equal to 0. So this one's going to definitely be allowed, and it seems to be intense enough for us to have a good-sized peak. Let's just go back to the spectrum and show it. Here's this peak right here. So the nu 3 plus nu 4 is pretty big intensity. Okay. The reason the CH stretches are so small is because this is taken on the ATR, and the attenuated total reflectance does not have a linear response. It's based upon the frequency. The penetration depth penetrates deeper at low frequencies. And so down here, you're actually sampling more of the sample than up here. So it's kind of like a path length difference. Even though it's not going through the sample, it's like the trampoline. That trampoline affects the low frequencies, or low frequencies can respond better to the trampoline effect than the high frequencies. And so it really favors these low frequency peaks, kind of makes them artificially taller. So that's an effect of the ATR. But still, the nu 3, nu 4 combination band is pretty intense, so we can easily see it. Let's look at the nu 7 plus nu 8 combination. So here again, we're going from 7 and 8 equals 0 to 7 and 8 equal 1. All of the other quantum numbers, 1 through 7 or 1 through 6, are 0 and 0. So we're just not showing those in the symmetry analysis. So we have A1 for the 7 and 8 being equal to 0. We're using Z polarized light, so that's A1. And then 7 and 8 are both excited by one quantum, and so that gives you the symmetry of the motion. Those are E modes, and so we have 2 E's over on the far left due to quantum states 7 and 8 being excited. So doing these pairwise from the right, A1 equals A1, A1 times A1 equals A1, and then A1 times E equals E. And so now we get to the interesting row where we look at the direct product table. We have E times E giving this combination of A1 plus A2 plus E. Same thing we saw in the CO2 actually. So only the CO2 was centrosymmetric and it had G's and U's on it. This one is not. It doesn't have an inversion center, so we don't have the G's and the U's. So E times E gives us this full combination of A1 plus A2 plus E, which contains the top row meaning this one is allowed. So that integral is not equal to 0, meaning it'll have some intensity that allows this spectral peak to show up in the infrared. So this combination is supported. Let's do one more. So let's look at XY polarized light hitting this combination band. So this first one we did was with Z polarized light. Let's look at XY polarized light. And so now we have another E in the middle. So we have 7 and 8, which are both A1 because they're in the ground state. Light, which is E, and 7, 8 in the excited states, both E. So we do these pairwise from the right. A1 times A1 is A1, A1 times E is E. And so now it's interesting, we have 3 E's. So the first two are straightforward. We have, again, this E times E gives us this square right here, A1 plus A2 plus E. And now we have E, and it's just like math. I mean, it is math. It's distributed through the parentheses. So it's E times every one of those pieces. So E times A1 is going to give us this row. E times A2 is going to give us this row. So we're going to get a couple of E's. And then when E times E, we're going to get all 3 of these. So we should have 3 of these E's right here, and an A1 and an A2. So that's what we have. We have an A1 plus an A2 plus 3 E's. So we have 5 functions here that have these symmetries. We have a wave equation that has A1 symmetry, one that is A2 symmetry, and 3 different ones that have E symmetry. And when we integrate that over all space, the one that has A1 symmetry gives a non-zero integral. Okay, the others are odd, they give 0 integrals, like some kind of thing where it's, you know, the integer multiples of pi are 0, just like we did in Calc Week. Yeah, yes.
Why did you change the light from Z to XY?
Just to see if XY was allowed. So we got this motion, this strange motion in the molecule. We know that Z can be absorbed. Can XY light be absorbed? And the answer is yes. So since it contains top row, then XY light can be absorbed by this combination too. That's also what contributes to its intensity, because your spectrometer is letting all kinds of light go through, polarized in all directions, and then your molecules rotated in different directions too. So this is essentially non-polarized light can be absorbed by this molecule. Let's say that XY polarized light was not allowed, but Z was allowed. That cuts the intensity of that peak by 1/3, because you're taking away 2/3 of the types of light that hit this molecule. So 2/3 of the molecules and 2/3 of the photons of light are going to be wrong, and only 1/3 are going to be aligned right. And so that's going to affect the intensity. And so if you only have one type of light that's absorbable by the molecule, you'll have a lower intensity. You still won't really know what that intensity is, but it's going to, all things being equal, it's going to be smaller than a motion that allows all 3 types of light to be absorbed. Okay. We have a choice. We could do the Kahoot, which is just testing on some of these things, or we could go look at the homework and I could talk about the test. Homework and test? Okay, so you can try the Kahoots on your own. Go to Kahoot and type in chem_prof, and you can find all my Kahoots, and that's a great way to test yourself on the lecture material. Get with some friends and have a contest. It's always fun. Okay. So this is the homework, and I will kind of guide you through the things that will definitely be on the test and things that I just was testing you on the homework just to see if you could like refresh your memory from organic and things like that. Like these bottom 3 questions, just asking about where the CH stretches are, CO stretches, C double bond O. That was just sort of a review from organic. We're in the mid-infrared region. You ought to know as a chemist where a carbonyl stretches. You ought to know as a chemist where a CH stretch shows up, okay? That's just put on the homework just to make you review. It's not on the test. But the degrees of freedom are on the test. And let's see, centrifugal distortion. Again, what is that? That's the bond stretching as the molecule rotates faster. So centrifugal distortion causes the bond length to increase as the vibrations or rotations are going up. This anharmonicity, what's going on with anharmonicity? It's not causing the molecule to rotate faster. It's not. It does cause one of these. Does it change the reduced mass? No. Remember, if we have a harmonic oscillator, we have this parabola here that's a function of, I'll just say R, which is distance, or bond length. Since it's symmetric, no matter where the molecule is in its wave functions, notice this RE, the equilibrium bond length, is the same straight up, right? Because it's centered in that harmonic oscillator. Anharmonicity is when this thing breaks the harmonic oscillator. And so now these wave functions are stretched out over this longer distance, and the bond length goes like this. Eventually it goes out to infinity, which is the dissociation of the bond. So when we have an anharmonic potential, what's it doing to the bond length? It's making it increase. Yeah, it's allowing it to spend further time away. The atoms are spending more time further away from each other. So that would be C. Any questions on the degrees of freedom? Translations are always 3 and only 3. Rotations depend upon if it's linear or not. So here it's asking about a linear molecule. How many rotations are there in a linear molecule? 2. Exactly. And then, so then in this particular case, formic acid, how many vibrational degrees of freedom? So we have 1, 2, 3, 4, 5 atoms. Okay, so 3 times 5 is 15. This is not a linear molecule, so subtract 6, we end up with 9. Okay, so then we get into the row vibrational peaks, definitely on the test. So you need to know how, this designation works. So let's just take this one right here, O2, and break it apart, right? What does the O tell you? O means Raman. Delta J is what for an O transition? Minus 2. Okay, so that means that, and this little 2 here, what does that mean? That is the J double prime. So that tells you what the lower state is. So this says that J double prime equals 2 and delta J equals minus 2. That's all you need. That's all the information you need to know that this is going from 2 to 0. Okay. So this is the J quantum number. What's the V quantum number for this transition? 0 and 1. Right? It's a vibration and a rotation change. So V is going from 0 to 1, J is going from 2 to 0 for the O2 line. Okay. What is the Q? Q means delta J equals 0. Yep. And the S, delta J equals plus 2. And then this subscript is J double prime. So you should be able to figure all of these out. I don't want to do all the homework for you, but this is the basic thing. Okay, let's look at this principle of mutual exclusion. I just mentioned that. Which molecule is centrosymmetric? And what does centrosymmetric mean? Yeah. Centrosymmetric means it has an inversion center. And so OCS, again, those two atoms are not the same on the outside, so it's not. Water is bent. There's no inversion center there. Acetonitrile, I just drew it. It was a really complicated C3V molecule. So CO2 is the only one that has an inversion center, and so that's for sure. The rule of mutual exclusion applies to CO2. Okay, spacing between the row vibrational lines in an infrared spectrum. Okay, think of Hamlet. What did he say? Right, 2B in the infrared, and in the Raman, 4B. Okay, that's great. Okay, so the approximate reduced mass of HCl, 37. Okay. Let me draw this molecule first. So we got a big old chlorine and a tiny little hydrogen. Okay. If this thing's going to vibrate, what's going to really be vibrating? It's going to be the hydrogen. Okay, so the reduced mass is a way to take the motion of two bodies and reduce it to the motion of one body. And in the HCl, it's so, the masses are so different that it's just the hydrogen moving. And so the reduced mass ought to be close to the mass of hydrogen. Okay. And we can show that by just looking at 1 times 37 divided by 1 plus 37. Right? Do you see how the 37s essentially cancel? It's 37 divided by 38. Okay, so that's very close to 1. And then that's going to be 1 gram per mole. How do I get to the mass of hydrogen if I haven't remembered it, or if I haven't memorized it and I haven't put it on my note card? How do I get out of this to kilograms? I divide by Avogadro's number. 6.022 times 10 to the 23rd per mole. Okay, so that gets out of the per mole. And then I've got grams and I want kilograms, right? So 1,000 grams is a kilogram. So that gives me the mass in kilograms, which is going to be the 1.6 times 10 to the minus 27. So you should be pretty quick in getting out of grams per mole and into kilograms and back and forth. Okay. All right, let's get to the row vibrational interpretations of this peak. Had some good questions on email about this, just the different confusions about the technique. Where is the vibrational frequency on this spectrum? Is it up here? Is it down here? Where is it? So the vibrational frequency. These are row vibrational lines. So where is it just the vibrational difference? So when we have this harmonic oscillator potential, and this is V equals 0 to V equals 1, that frequency is the vibrational frequency, and that shows up somewhere on this spectrum. But there's no peak associated with it because it's a diatomic, or yeah.
So it would be in that Q area?
Yeah, it's right here where the missing Q branch is. So this is new. We could call it new 0, I guess. So it's because it's the vibrational frequency starting in the 0 state. So we'll call it new 0. And so how do I get the value for that when there's no peak there? Well, I could pick any one of these pairs and just average them. Okay, so I could add, here's saying use the R0 and P1 lines in the HCl spectrum for the H37. So the person was like, how do I know which one of these little doublets is the 37 versus the 35 isotope? So how did you solve that problem, if you even considered it? Any ideas? Okay, look at the periodic table. What's the mass of chlorine? 35 or what? 35.5, really. So it's not perfectly 35, but it's closest to 35. So that tells you the most abundant isotope for chlorine, given the two combinations of 37 and 35, is 35. In fact, it's 3/4 of the way to 35, and so it ought to be like a 4-to-1 ratio, you know. So it's going to be mostly HCl35. So 37 isotopes are going to be the smaller peaks. So these are 37s, and these are 35s. So all the smaller peaks are the HCl37s. And so we would use these two right here. Okay, and so that's going to be, which one of these is the R0? So over here, this is the high side. So this is R0, and then this is the low side. So this is the P branch, so this is the P1. Okay, so we just take those two frequencies, add them together, divide by 2, and we get the vibrational frequency. So it's 28. I don't know, which one was it? Do you remember? It was A? Okay, yeah, just these are so close together. Yeah, I wanted you to really have to figure out the correct lines to use, and so it's A. Okay. All right, and then use the R0 and R1 lines to get the rotational constant. So R0 and R1, so this is R1 for 37. So I take the difference, and that difference here is 2B. So I take those differences, and that's 2B. So I just take the difference and divide by 2, and I get, what does it come out to be? Is it 9.8? Yeah, I was thinking it was 9.8. Okay, and then using the figure above, what's the designation of the 2821 peak? So I'm just sort of figuring out which one to label. 28, 21, where is that? Right here, okay, this one. All right, so it's a 35 isotope, okay? And so it's not going to be the 37s. And it's P1, P2, P3. So it's the P3 for the 35. So 35 P3. But you see the logic there? It was the largest one because it's a 35 isotope, and it's the third P line. Okay. I put P2 in here as a possibility in case you mistakenly thought it started with P0. But you can't, since P is a delta J minus 1, you can't start at 0 because it would go to negative in the upper state, and you can't do that. So it's always P1 is the first P line, R0 is the first R line. Okay, so then we solve for the bond length using our 16.8 or whatever that constant is. And I just gave you a different rotational constant just so it sort of breaks your coupling from this question. I didn't want you to have the answer for this question in the question down here. So if this is the correct bond rotational constant for this molecule, what's the bond length? Okay, so yes.
If they were reversed on the spectrum, would R still start at 0 and P start at 1?
Yes. Yeah, so it's always, because that's the delta J business. Yeah, so R since it's a delta J plus 1, it can start at 0, but P can't. Okay. This, and the only trick on this problem is just the units, making sure you cancel out the, like you calculate the reduced mass correctly and so on. But if you use that note card equation, then it's pretty straightforward. I did include a couple of these just to get you ready for the lab. So the coefficient of variation is the RSD times 100%. Okay. And what's the RSD? RSD is equal to the uncertainty over the average. And so here we have this rotational constant written out, 10.75 plus or minus 0.25. So it's 0.25 over 10.75 times 100%. Okay. So it's pretty good because it's, this is already in the third significant digit. Okay. 1% would be 0.1, and so it's about 2.5 times that. So it's, about 2.3%. So now, if the RSD of the rotational constant is 20, what's the RSD of the bond length? Okay, so this one requires some propagation of uncertainty. So if you go through that lecture and look that up, you can see that the bond length is equal to or proportional to, let's do proportional to, the rotational constant in the square root, right? So that's proportional to the rotational constant to the 1/2 power. So there's in that propagation of uncertainty, you have the RSD of y is equal to that power x times the RSD of x. And so I don't have that lecture available really quickly here, But that's one of the examples. Okay, now to ease your mind, it's 8:44, so we're running out of time. To ease your mind on the exam, the propagation of uncertainty is not on the exam until I have it in the lab. And so you've got to use this for the lab in 2 weeks. And so it'll be on the test after that. Okay, but I put it on the homework just to get you ready for the lab. So you don't have to go through and hammer your way through and spend your study time on the propagation of uncertainty for this exam, which is in a couple of days. But we'll come back to it and check those lectures out that are online. Okay, then we get into the stuff that we did today, talking about overtones and hot bands and stuff like that. So if the vibrational frequency is 2880, what's the frequency of the first overtone? And so we're just doubling that, okay? And so we're doubling that frequency, and so we get something close to the 5760. The first hot band is going to be 2880 because for vibrational frequencies, it's an equal ladder of states. Everybody say that with me, equal ladder of states. Just like the rungs on a decent ladder are all equally spaced, okay, the same with vibrational frequencies. That'd be a really weird particle in a box ladder where the first rung and the second rung are 1 unit apart, and then 3 units apart, and then 5 units apart. You couldn't climb very high because the rungs would get too far apart. But for vibrational frequencies, the hot bands are all the same frequency as the fundamental, because this distance right here is the same as this distance right there, and it's the same as that distance. So all 3 of these frequencies are going to be the same. So the hot bands all show up at 2880 if there's if the fundamental is 2880. So that's the feature of vibrational spectroscopy, at least as far as harmonic oscillation. When it gets to anharmonicity, it starts to tail towards the lower frequency side because the spacing gets smaller. Okay, combination bands. Here we've got new V1, V2, V3. So we just double that middle one. So we take this frequency times 2. And then add them all up. So we have 1 of those, 2 of these, and 1 of those to get that combination band. Okay. And then here we have that symmetry thing where we're taking, you know, A1U times A1G is A1U. Then E1 times A1 gives us an E1. U times U is G. And then we have E1U times E1G, which is going to give us that A1 plus A2 plus E1, and there's going to be G times U, which is going to be U, U, and U. And so I get all U's, it's not going to be allowed, okay, because it's not top row. I could have looked at this at the very beginning and counted up the number of U's, and see I have 3 of them. That's an odd number. So I know it's going to be U in the end. So if you have an odd number of U's, then it's not going to be allowed because your end result is going to be, think of it as -1. -1 times -1 times -1. You're going to get -1. So that's not an even number. And so that's the homeworks. The only thing that's that I want to emphasize that the homework didn't really have much on was the electromagnetic spectral regions. Know where the rotation occurs and the vibration occurs, and like UV vis and so on. So have a look at that. Also, it's in the notes, but I just want to make sure you remember that this gas phase, rotation, vibration stuff only happens in the gas phase because you got to have a freely rotating molecule. Makes sense? And then for pure rotation, you have to have a dipole moment. So if you have a symmetric molecule like CO2, you don't have a pure rotational spectrum in the microwave region. You have to have Raman to do like a diatomic, homonuclear diatomic like nitrogen or oxygen or CO2. If it's a symmetric molecule, you only have Raman that can give you the pure rotations. But the rho vibrations, where you have it in the infrared, vibration added to rotation, you can see that as long as it's in the gas phase. Let's see. Know the PQ and R branches and O and S branches and what they do. Reduce mass. Just be good with all of those equations for vibration and rotation. And that's pretty much it. Oh, and the arrow diagrams, practice that again where you assign a symmetry to them. So like if all the arrows are kind of going in the X direction, then it has X symmetry, go to the character table and find that symmetry. Okay, so I pulled that forward from the last exam onto this one also because this is the vibrations and we have those arrow diagrams. So, you know, when the bond angles are changing, that's a bending mode. When the bond lengths are changing, that's a stretching mode. So just, that's common sense. So think about it. If it's the bond is stretching and the arrows are going out, that's a stretching mode. But if they're 90 degrees to the bonds, that's a bending motion. And I think that's a good review. It's all on video. You can go back and catch these last few comments.